So when thinking about this Pythagorean, we have sine squared plus cosine squared is 1. It's important to remember that exponents don't distribute over sums. I can't just take the square roots of the sine squared plus cosine squared and come up with sine theta plus cosine theta. So if we pull this back into algebra, exponents do not distribute over sums. So the square root of x squared plus y squared is not just x plus y. This is the same principle as x plus y squared, the square of the sum of x plus y, not being equal to just x squared plus y squared. When I take x plus y squared, and I have to have an x plus y times another x plus y, we've got to multiply all that out. So if we want to think about what this is related to, imagine taking a number and squaring it. Imagine I wanted to take the number 23. Now let's not use 23. Let's use something without 2 in it. Let's just think about taking the number 17 and squaring it. So this is 17 times 17. And when we multiply 17 times 17, I've got to multiply 4 things. So if we just think about our standard algorithm, which is awful, but is the one that we've all been programmed with, we do 7 times 7 is 49. 7 times 10 is 70. 10 times 7 is another 70. And then 10 times 10 is 100. So we get 100, 2 70s, and a 49. Or 289. So there are those 4 things that we have to come up with when we square the 17. This is because the 10, the 1 in the 17 represents 10, one group of 10, and the 7 represents 7 groups of 1. They're different terms. So what we're doing is we're taking 17 squared and thinking of it as a 10 and 7 and squaring that. So when we multiply, I have 10 plus 7 times another 10 plus 7. And if we think about it in those terms, if we think of numbers as just being polynomials, where x is always equal to 10 because of the way we count, here are the 4 terms. We get 10 squared, or 100, plus 70, plus another 70, plus 49. So we can't just square the 10 and square the 7 and say it's 149. We'll be missing out on 140, right? So we wouldn't say 10 plus 7 squared is 10 squared plus 7 squared. And we can see exactly what we're missing. We're missing the 2 copies of x times y. We're missing 2 70s, which is 140. So we're missing the 2xy, which is 2 times 7 times 10. And we can see that 149 is off of the 289 by 140. Now this is, in this case, I wrote 17 as 7 and a 10. But we could also think of 17 as being 20 negative 3. This is just a side note. I could think of 17 as 20 negative 3 if we allow a little bit more liberal application of what can be a digit. And here we just start counting down from 400. So 20 times 20 is 400. 2 times 3 is 60. 20 times 3 is 60, minus another 20 times 3, which is another 60, plus 9. So here we have 409 minus the 120, which is 289. This gives us kind of a broader view of how numbers work. This is why we study algebra, so that we can have a better picture of how numbers work. Because none of the rules in algebra are some weird, arcane rules that you have to memorize. This is just how numbers work. And once again, we can't just square the two terms, 20 minus 3 squared is not just 20 squared minus 3 squared. First of all, the minus 9 will be going in the wrong direction because it's a negative 3 that's being squared. And second of all, we'll be off by those two negative 6. So we know that this applies for exponents of 2. The square root symbol is just another exponent. So it has to follow the same rule as the exponent of 2. The square roots. So the square root of x squared plus y squared is x squared plus y squared to the 1/2 power. It's just another form of a square root. I don't know why we started using this radical notation before. I don't know who started this radical notation business, but radicals are just exponents. So they follow the same rules as exponents. Radicals are exponents. So radicals also do not distribute over the sum. Any questions? This is actually an important aspect of things that we try to do in math, especially at this level, even all the way through calculus, dealing with exponents being applied to sums. So in trigonometry, in calculus 2, when y'all are in calculus 2, even though everybody here is future calculus students, when y'all are in calculus 2, you're going to learn a process called trigonometric substitution. Trigonometric substitution is going to be using this Pythagorean identity to take two terms, 1 minus sine squared, and replace them with one term, cosine squared. Because if I have the square root of 1 minus sine squared, I can't just drop the exponent. If I have an expression that says the square root of 1 minus sine squared, I can't just drop the exponent, but I can replace the 1 minus sine squared with cosine squared. And now I don't have a sum. Now I can apply this, I can cancel the square and the radical. The square root of cosine squared is going to be cosine. So here, I can't simplify anything. In that first line, I can't simplify stuff because the exponent is applying to a sum, two terms. But if I replace 1 minus sine squared with one term, cosine squared, now I can take that cosine squared and raise it to the 1/2 power. We'll find the square root of cosine squared. Two terms, stuck with the radical. One term, apply the radical. Two terms under the radical, nothing we can do. One term under the radical, we can apply the square root. So when there's two terms under the radical, there's nothing we can do. The radical stays. But if I could take those two terms and combine them into one term, I get to apply the radical. I can get rid of the radical and simplify my whole expression. Then someone can come along and be super pedantic and say, well, actually, square root of something squared should be the absolute value. You just respond to pedantic manner. Okay, fine. When does that matter in the problem that we're doing? We'll go. Any questions? These are the kinds of things that we miss out on when we're focused on learning algebra as a bunch of just process. We don't really take the long view of why we have a process, a given process. And we don't have proper perspective on treating radicals like exponents and treating exponents and learning distributive properties properly, so that we learn things that we don't, so that we don't try to simplify the square root of x squared plus y squared as x plus y, because that makes sense. The square root of something squared, you've told us those were inverses. Why can't I just apply it to each of the terms of sum? And the answer is that's just not how numbers work. That's not a satisfying answer. It doesn't really explain anything. But when it comes down to algebra, when you ask, why can't I do this? The answer is probably because that's not how numbers work. That's not how addition and exponents interact with each other. That makes sense? I usually summarize it by saying, you forgot to FOIL. In a perfect world, I would say you forgot to FOIL, and you wouldn't know what the F I'm talking about when I say FOIL, because that would just be multiplication, and you'd learn distributed properly. But for the most part, we FOIL our polynomials and we multiply our numbers. And I'm like, oh, son of a bitch, it's the same thing. Emphasize the interaction between addition, multiplication, and exponents. And then it'll be clear that we can't do this because we'd say, oh, wait, that radical is an exponent. And that's not how exponents apply to sums. Yeah. Yeah, we're just using our Pythagorean identity up here. If sine squared plus cosine squared is equal to 1, I can solve this for cosine squared by subtracting sine squared from both sides. So I'm just rewriting this as cosine squared theta is 1, and then put the sine squared on the other side, minus sine squared. The big advantage here is that two terms get combined through an identity into one term. And that one term, we can get rid of that. With two terms, stuck with the radical. With one term, we can simplify the radical. Two terms enter, one term leaves. No one's seen Mad Max Beyond Thunderdome, so I don't know why I keep bringing that up. Has anybody seen Mad Max Beyond Thunderdome? Mad Max 3? Did you know that Mad Max Fury Road is like Mad Max 4? A little bit of a reboot. Yeah, Mad Max 3 Beyond Thunderdome. Mel Gibson and Tina Turner. Don't watch this movie. It's not good. So. How about The Road Warrior? The original Mad Max movie. I think it was Road Warrior first and Mad Max second. I can't remember. They're awful movies. You probably shouldn't watch them. But it might be that I'm trying to get you to watch the movies by telling you not to watch them. Very underhanded. If you're surprised that I'm being underhanded, dude, I'm a fucking teacher. What did you expect me to do? My job is to manipulate you. I'm trying to make you learn math against your will. I'm trying to trick you into learning math. So. Honestly, I like Road Warrior too. I don't think it's a good movie in the sense of a good movies, but I mean, all right. My favorite part of Road Warrior is that If you watch Road Warrior, it's an Australian movie. And it's got Mel Gibson. He's Australian. They dubbed his lines. You watch him, and he like when you watch him talk, they had to dub some of his lines because he's Australian, and he was speaking like an Australian. And like, well, people in America are not going to understand what the F he's saying. Like, oh, are Americans that dumb? And like, oh, let's just dub the lines. You didn't answer my question. I think that. I think that. You can't refer to the Philosopher's Stone. No. Change it to something magical so Americans will understand. Do you know what I'm talking about? Stupid Americans. No, it's the Philosopher's Stone. Do they call it the Professor's Stone? Yeah, in America, it was the Sorcerer's. They had to change it to the Sorcerer's Stone because philosopher is too fancy. Americans would reject it. So let's do some homework problems. All right. Okay, so in this case, we are going to be using some. The idea here is that we want to use some identities. So we've got this expression y is equal to 4 times this fraction sine of 2t minus pi over 2 plus 1 all over 1 plus cosecant of 2t minus pi over 2. They're just brackets. And time at t is time in seconds. And we want to simplify the equation. And you can see what we're going to end up with. But what we want to notice are here are the two things that stand out right away. First of all, I've got a cosecant of 2t of stuff, cosecant. So we see cosecant in an expression. There we go. So here are the things that we notice. This expression has cosecant in it, and it also has sine in it. Plus 1. So we want to find some identities that we're going to notice right away. And I noticed a cosecant of 2t minus pi over 2. So this reminds me of the identity cosecant of theta is 1 over sine theta. I also see that my sine and my cosecant are sine of 2t minus pi over 2. I have sine of 2 terms. So this is reminding me of the identity sine of A minus B is sine A cosine B minus cosine A sine B. Because of the pi over 2, it could also be reminding me of some co-function identities, but this is the one that jumps out. It's sine of a difference, so I can use a difference identity sign. Sine of A minus B is sine A cosine B minus cosine A sine. In this case, A would be the 2t, and B would be the pi over 2. What this would do for us is simplify our expression. Instead of having sine of a difference, We just have sine of A and cosine of B. The advantage here is that it's 2t minus pi over 2. So I just have to know what the cosine of pi over 2 is, and then the sine of pi over 2. I'll be able to simplify my expression that way. Other things that I noticed that might be in play here is that there's a sine of 2t. So that makes me think of the double angle identity for sine. That says sine of 2t is 2 sine t cosine of t. So these are all the identities that I see might be in play here. Not are going to be, but might be in play. Now, if we look at the answers, we can see what the answer is marked here on my screen. But if we just look at the answers, notice that all of the answers have a 2t in them. All of the answers have a 2t in them. This suggests that we're not going to need the double angle identity for sine. So even though I'm reminded this cosecant says, going to use some reciprocal identities. Ooh, sine of a sum, that means we're going to use some sum and difference identities. But since all the answers have a 2t, we're in terms of 2t, probably not going to need this one because of the form of the answers. So we're probably not going to need the double angle identity considering our selection of answers. If our selection of answers had stuff like cosines of t and sines of t and not 2t, then I would think I'm definitely going to be using this sine of 2t figure. Now, before we start getting into the details of trying something and seeing what happens, this is where we kind of begin. We take a look at the expression that we have to deal with and see what's here and what do I know about those things. What does cosecant make me think of? Cosecant makes me think of reciprocal identity. Sine of stuff of multiple terms makes me think of sum and difference identities. So those are the things that I'm going to apply. Now it's going to be mostly algebra. The first thing I noticed was this cosecant. I'm just going to grab this denominator. Let's see what happens with this denominator. So what happens with this denominator? I've got 1 plus 1 over sine of 2t minus pi over 2. So I'm going to grab the denominator. I'm going to apply the reciprocal identity. I don't know if this is going to help. I'm just going to try some stuff. This is sometimes the hardest part of doing math problems. Grab some stuff and try it. So I'm going to grab the denominator and I'm going to use a reciprocal identity. Now I'm going to look at that sine of 2t minus pi over 2. I'm going to see that there's 1 in the numerator. Let's see if the sine of 2t minus pi over 2 becomes anything. Now I'm going to take this denominator part here, this piece of the denominator, and I'm going to use my difference identity for sine. So sine of 2t minus pi over 2 is going to be sine of 2t times the cosine of pi over 2 minus cosine of 2t times the sine of pi over 2. The advantage of doing this is that our arguments go from being 2t minus pi over 2 to just 2t pi over 2. The other advantage is that it pulls out cosine of pi over 2 and sine of pi over 2 as just factors. And those are constants. In particular, cosine of pi over 2 is just 1. And sine of pi over 2, cosine of pi over 2 is 0, and sine of pi over 2 is equal to 1. Pi over 2 is 90 degrees. Cosine starts at 1, drops down to 0 in the first quadrant. Sine starts off at 0 and goes up to 1 in the first quadrant. So this simplifies some stuff for us. This whole term 2t times cosine of pi over 2, that just drops out, and we just have minus cosine of 2 pi. 2t, not 2 pi. Yeah. Yeah, I'm using the difference identity for sine because my expression is sine of 2t minus pi over 2. That gets multiplied by the cosine of pi over 2, which is 0. So the sine of 2t drops out. Sine of a minus b. So this is what our denominator looks like. This is just the denominator. It's not the whole fraction, just the denominator. Now, I look at this and I don't like it. It's 2 fractions, and I know this is the denominator. I don't like 2-term denominators. So I'm just going to get a common denominator. I'm going to write 1 as cosine of 2t. Oh, I wrote pi again. Oh. This is cosine of 2t over a cosine of 2t minus 1 over a cosine of 2t. So I'm just going to write this as 1 fraction, cosine of 2t minus 1 all over cosine of 2t. Remember, this is sitting in the denominator of that big fraction. If I'm going to divide by a fraction, I want 1 fraction. I don't want to divide by 1 minus. 1 minus 1 over cosine of 2t. I want to multiply by the reciprocal of this fraction. This goes back to the discussion we had earlier when we had the square root of 1 minus sine squared. That's inconvenient. If I replace 1 minus sine squared with cosine squared, square root of cosine squared is just cosine. If I ask you to divide by 2 3/4, you would take that 2 3/4 and turn it into an improper fraction. So it's not multiple terms. So the reason I'm saying two-term denominator, no thank you. Imagine if I had 5 divided by 2 3/4. 2 times 4 is 8 times 3 is 8 plus 3 is 11/4. Your strategy, besides just grabbing a calculator and saying what's 5 divided by 2.75, is to write the 2 3/4 as a mixed or as an improper fraction so that you can multiply by the reciprocal nice and easy. So this is 5 times 4/11, 20 over 11. Any questions? Do we agree that this would be our plan if we had to do this by hand? Like, oh no, I have a TI-84 and it can convert things to fractions. I would totally just be like 5 divided by 2.75 and then convert it to a fraction and act like I wrote. What we're doing here, when I change that 2 3/4 to 11/4, it's the same reason that I want to change 1 minus 1 over cosine of 2t to cosine of 2t minus 1 over cosine of 2t. Because what we're looking at here is 5 divided by 2 3/4. That 2 3/4 written as a mixed number is a two-term denominator, and we didn't like it then, so we don't like it now. And we did exactly the same thing. 4 times 2 is 8, plus 3 is 11. That's my new numerator. Cosine of 2t times 1 minus 1 is cosine of 2t minus 1, and that's my new numerator. We did the same thing. Any questions? Remember, this is also an algebra class. That's why it's that's the 8:30 part coming in. Also an algebra class. Stuff out. You got to get the algebra in there too. Yeah. No, we used sine of A minus B. Okay. So if you could write it as sine of A plus a negative pi over 2, and it would work out the same. This is just the denominator. I wanted it as one fraction because this is a mixed number. This is an improper fraction. As a denominator, improper fraction is better than mixed number. 2 terms in your denominator, mess. 1 term in your denominator, nice. If you're thinking, man, I should have taken an algebra class, you wouldn't have remembered from an algebra class, so it's okay. I would have reminded you the exact same way. Now, this is just the denominator. Let's grab the numerator. And now the numerator. The numerator was sine of 2t minus pi over 2 plus 1. And we're going to do the same thing that we did in the denominator. I'm going to take that sign of the difference and use my difference identity. I still don't know if this is going anywhere. We're just trying stuff. There's going to be sine of 2t times the cosine of pi over 2 minus the cosine of 2t times the sine of pi over 2. Plus all plus 1. Here, the same thing happened as the last time we did this. Cosine of pi over 2 is equal to 0, and sine of pi over 2 is equal to 1. So all this is just equal to negative cosine of 2t plus 1. Any questions? Yeah, should have done this one. Oh. Let's look at our whole fraction now. Our whole fraction, our expression. So our sine of 2t minus pi over 2 all plus 1, that all becomes minus cosine of 2t plus 1. I'm going to change the order. The cosine of 2t is still negative. The 1 is still positive. I'm just going to write the positive one first. So I don't have to leave with the negative. I can write less. The denominator is this whole thing here. Now I can see I'm taking this 1 minus cosine of 2t and dividing by cosine of 2t minus 1 over cosine of 2t. So I'm going to take 1 minus cosine of 2t and multiply by the reciprocal cosine of 2t over cosine of 2t minus 1. The reason that I want to do this is because that 1 minus cosine of 2t is the opposite of cosine of 2t minus 1. So I can cancel those out as opposites. All this is still being multiplied by 4. If I divide opposites, if I take x minus y and divide by y minus x, that's negative 1. Not because of fancy algebra rules, but if I take 5 minus 3 and divide it by 3 minus 5, I get 2 over negative 2, which is 1. X minus y and y minus x are opposite. So 1 minus cosine of 2t and cosine of 2t minus 1 are opposite. Now cancel out to negative 1. So we end up with a negative. We still got this 4. And we still got this cosine of 2t. And they wrote it weird in your answer selection for brackets negative cosine of 2t. Which makes me wonder why they included the 4 in the first place, but Oh, wow. Yes. So one of the reasons I didn't want to multiply the cosine of 2t by the 1 minus cosine of 2t is I knew I was dividing fractions. Whenever you're multiplying and dividing, these things factor because you need to expect some stuff to cancel out. When you're multiplying and dividing, leave things factored. Say that again. Uh-huh. Yeah, they just wrote the factors in the weird order, and so they needed brackets around the negative cosine of 2t. No, because it's still 4 times the negative times the cosine of 2t. And that's all, I have all the elements here. 4 times the negative times the cosine of 2t. A times B times C is equal to B times A times C. Right. Because they are opposites. I have a positive 1 and a negative cosine of 2t, an x and a y, x minus y. And in the bottom, I have a positive cosine and a negative 1. So that's the form y minus x. So they're opposites. If you change the order in a subtraction problem, you get opposites. You could also think of factoring out a negative 1 from the numerator. Factoring out a negative 1 changes the signs. So it's negative 1 times cosine of 2t minus 1 divided by cosine of 2t minus 1. Yeah, the 4 just got carried along through the whole problem. So this is a trig problem because we had to recognize all the trig identities that were going on. But once we started using the trig identities, it became an algebra problem. All trig identity problems are just algebra problems in disguise. Not so much transformers, robots in disguise, trig formers, algebra in disguise. The right song for that. Trig formers, algebra in disguise. Yeah. It only looks like a mess because it is a mess. Because we were breaking things apart and like plugging stuff in the hopes that something would work. That's why I break it down into pieces. That's why I started off by just grabbing the denominator and seeing what we could do with that. Because otherwise, doing this all at once, doing this all at once, it becomes a much bigger mess. Because remember, this is just going to be the denominator. Put all these steps under these steps and kind of a lot. And then, so all this stuff up here goes from the top up here to the top over here. And from the bottom down here to this bottom down here, we did lots of steps. We did the reciprocal identity, the difference identity, calculated some, simplified some constants, and then got a common denominator. Any questions? All right. So this raises the question, which is a perfectly valid question. How would I know to do this? You do thousands of problems and you will just know. It just kind of comes down to that. How do I get better at this? You do thousands of problems. It's the only way. There's no secret formula for it where you have to do some kind of weird, strange ritual, sacrifice an algebra textbook, and all of a sudden you're better at algebra. You just have to practice. Now, getting to the point where you would recognize what to do, that requires lots of practice. I don't know how much, because it's different. There are 12 people doing 12 different ways that this could happen, in just of the people in this room. And that's for this problem. We move on to the next problem. We've got 12 more ways, 12 more rates at which you will become proficient at this activity. Why was I able to see what was going to happen in this problem? I have done thousands of problems. I started trigonometry when y'all were like negative 10 years old. Wait, when did I do trigonometry? I did trigonometry in the late. So some of you are like negative 20, 30 years old. And why is it that I'm good at this? Is it because I'm smart? 100% no. I can't possibly be smart. I've been doing the same job for the last 20 years. There is no way that I'm smart. I've not had to do very much for the last 20 years. I got better at teaching. That skill set has improved. There are certain things that I left behind my skill set of teaching. I go, you should do stuff on time. I'm like, oh, never did stuff on time before. Why would I start now? But there's no way that everybody in this room is not smarter than I am, just as far as like this computing power. Far more ability than I have. I just have experience. You know what I mean? That's the only advantage that I have. I know the stuff. That's why I'm standing here and y'all are sitting there. You know what I mean? All it takes is time. It's just a function of time. There's nothing that's going to physically stop you from learning to do this if you choose to learn to do this. But that's the first step. You choose to learn to do this because you're adults. And if you don't want to, you don't have to. The great news is if you're like, oh, you know what? I don't want to learn this. I am out of here. That's totally cool because if ever comes a time you're like, oh, actually now I want to learn this. Come on back. And I'll probably still be here because I can't retire at 51. I probably should retire at 51, but it can't. You know what I mean? And there should be like a cap on teacher age. Teachers become like, eventually teachers just become too disconnected from like reality. And I spend a lot of my time trying to be a teacher, learning kind of like intergenerational communication. Not like using terminology of younger people because then that just sounds stupid. It sounds dumb when old people use the language of young people. And you should make fun of old people when they start trying to talk like young people. Hey kids, let's rap for a minute. That's what they used to say in the 80s because I don't know. They thought that would make them seem cool, and we all just laughed at them. And that was the correct answer, because they were being dorks. So if I like come in here and start trying to talk like a 21st century 20-year-old, talk like a Gen Z or a millennial, I would sound ridiculous, and y'all should make fun of me for it. So, does that make sense? I can say that out loud, because if you do, they go, you sound like a dork. They go, you're right, I do. Some people might actually get all offended and say, well, no, I'm cool. I'm cool. I can be cool too. It's like, no, you cannot be cool. You are 50. Are you a rock star? No, I'm a math teacher. You cannot be cool. You know what I mean? It's like only one path for 50-year-olds to be cool. And you have to be a rock star. Fucking Mick Jagger's got a walker. Look at that guy. He's so cool. I don't remember my lyrics. Just kidding, Mick Jagger. Don't at me. All right, let's take a break, come back and do some other problems. Yeah, we'll take a break, come back and do some more problems. Oh, there's still more on this problem. Let's take a break and come back and finish this problem. There's a lot going on.